So we are doing the single random variable. This is engineering statistics and linear algebra. We were trying to solve some of the numericals associated with the chapter. Okay, we need to solve 73, but 73 I think I might have made some mistake in the solution over here. So we'll do that tomorrow. We'll take up the 74, numerical 74. The 74 is the random variable x is Gaussian with mu x is equal to 0 and sigma x is equal to 1. This is mean and this is standard deviation, and we are considering Gaussian. So because it is 0 and 1, we need to consider that this is normalized Gaussian random variable. Now the random variable y is obtained from x using y is equal to 10x squared. So we are writing an equation here. This is a function. So that means we are talking about function of the random variable. So we need to find out what is the value of fy for 0.1298. Okay. So to solve this, we need to consider the Gaussian random variable. And we need to consider the mu x. This is all given to us: mu x equal to 0, sigma x is equal to 1, Gaussian random variable, and y is equal to 10x cubed. So if y is equal to 10x cubed, then x will be equal to, you can take this 10 over here, then it will become y by 10 is equal to x cubed, or x cubed is equal to y by 10, and x will be equal to the cubed root of y by 10. X will be equal to the cubed root of y by 10. So this can be solved as y by 10 is equal to x cubed, or x cubed is equal to y by 10. Therefore, x will be equal to cubed root of y by 10. We know very well that the cumulative distribution function for y, fyy, is equal to p of y less than y. Now this y over here, okay, this is basically equal to, we can try to write the value over here if we substitute it for x correspondingly, right? So we can try to write over here that will give us the value of y is equal to p of y less than y, and this y less than y will in turn give us the value x less than the value of x, and that x less than the value of x is equal to cubed root of y by 10. This is cubed root of y by 10. fyy is equal to fxx is the standard format. fyy is equal to fxx, and fyy is this value. Fx, what you call x, will be equal to p of x less than x, and that value of x is nothing but the cubed root of y by 10. So having written this, now we need to find out the value of fy, 0.1298. This is the value which we need to find out, and hence we need to write here p of x less than or equal to cubed root of 0.1298 by 10. So this value we need to find out. Now this value, cubed root of 0.1298 by 10, turns out to be 0.235. Using the calculator, you can calculate it, and this turns out to be 0.235. And from the table, we'll get this value as 0.5929. So this we can see in the table, and the table might be there in over here. Okay, in this we can just see where we have written the table. Okay, for the Gaussian random variable, yes, this is the table. So from here we can try to find out what is the value corresponding to 235. Is it 235? Yes, it is 235. So when x is 235, what is the value of the probability corresponding to that is what we can try to find out. So 0.2, this is 0, this is 1, this is 2, this is 3, 0.5 will be exactly in between. So 0.5910 and 0.5948, exactly in between, because it is 0.23, 5. So exactly in between over here. So exactly in between means you can find the interpolation of this, and that will be the difference between these two will be naturally 0.0038. Half of that will be 0.0019, and that has to be added to this, and that will give us the value 0.5929. 0.5929, and that is what we have here in the solution. Okay, 0.5929. Okay, again I'll repeat. Okay, so 0.23 is 0, 1, 2, 3. Okay, 5 means 2, 3, 5. If you say, it will be between 0.23 and 0.24, exactly in the middle. And middle of this is naturally the average of these two. You can take average of these two also. Okay, this plus this divided by 2 will give us the value, which will be 0.5929. Okay, average of these two will be 0.5929. That's another way, rather than whatever interpolation formula which we might have used. Okay, so exactly in the middle means we need not find exactly the interpolation. We can just take the average of these two, and that will be the 0.5929. Now let us go to the problem number 77. Okay, 75 and 76 are similar to the earlier problem 74, so one can solve this. So we'll go for now 77. You can see here that 77, 78 and 79 all are similar. So we have picked up here 77. You can easily solve, once we know how to solve 77, we can easily solve the 78 and 79. Okay, so find the transformation y is equal to gx that will convert the random variable x, which is uniformly distributed between 0 and 1, into the Cauchy's random variable y. So uniformly distributed between 0 and 1 will be giving us the uniform distribution, but we need to transform into the Cauchy's random variable y, and the description for the Cauchy's random variable is given in the appendix A. Okay, so going back to the appendix A, so we can try to find out where this Cauchy's random variable is, and correspondingly take that and try to solve it. So we have the Cauchy's random variable here, right? This is the what you call the PDF, and this is the CDF. So we might take this CDF and try to solve it and get the value. Quite simple over here. We can go back to that and then see what we are trying to do. Okay, so now we have here the value fxx is equal to, for uniform random variable, it is 1 between 0 to 1 and 0 otherwise. Fxx is x between 0 to x, 0 less than x less than 1, 0 for x less than 0. And really speaking, we should write it a little differently. There is a mistake which I might have done here. So x is, this is all right, whereas this I should write 0 for x less than 0 and 1 for x greater than 1. 0 for less than 0 and 1 for x greater than 1. Okay, we can go back and check over here in the uniform random variable how we have written for this. Okay, and then we'll be able to make out what is the way in which it is written. Okay, what is the way in which it is written. So you can see here 0 for x less than a, x minus a by b minus a between a to b, 1 above b. So our a is 0 and b is 1. So therefore 0 for x less than 0, x by 1, x minus 0 by 1 minus 0 will give me x only, and here 1 for x greater than 1, and this will be 0 less than x less than or equal to 1. Okay, so there is a small change in the what you call solution, but that doesn't make any change further. Okay, fyy is equal to fxx, and fxx we can take it directly from here, and fxx is the value x itself between 0 and 1. Okay, between 0 and 1, so we need not write this minus infinity to infinity. We can as well write 0 less than x less than 1, and that's what we have written over here. Okay, here also we can write 0 less than x less than 1. Okay, so fyy is directly the Cauchy's random variable. For x we have the Cauchy's random variable, just we have seen. Okay, we have seen the Cauchy's random variable for x over here. So in the same way we can write for the variable y. Okay, fxx is equal to 1 by pi tan inverse of x by a plus 1 by 2. Fyy will be 1 by pi tan inverse of y by a plus 1 by 2 for values between minus infinity less than y less than infinity. So in the same way, we can try to write over here. So here we have written 1 by pi tan inverse of y by a plus half is equal to x, because fxx in the uniform distribution which we have considered over here is x between 0 to 1, and that's why we have considered here between 0 to 1. Okay, so in place of this, also in place of the above minus infinity less than y less than infinity, we can write 0 less than x less than 1. So now rearranging this, 1 by pi, half can be taken on this side. We'll get, 1 by pi tan inverse of y by a is equal to x minus half. Okay, pi we can take on the other side. Then tan inverse of y by a is equal to pi x minus half. Y by a will be equal to tan of pi multiplied by x minus 1 by 2, and y itself will we need to take on the other side. We'll get the value of y is equal to a into tan of x minus half pi, where we need to substitute the value of x here. We need not bother what it is. Here also we can try to write 0 less than x less than 1, because at the end we are trying to represent y in terms of x. So we will get here 0 less than x less than 1. So thus we can, get the solution like this. Okay, so this is how we can solve it. So in the last class, we didn't solve the, problem number, I think 58. We didn't solve 58. Let us see the problem number 58. Okay, so problem 58 is this, right? So temporarily, I'll just stop the what you call plotting. So 58 is use the characteristic function of the Laplace random variable found in the appendix A to find the first two moments from the origin E of x is and E of x squared. With the results, find the variance sigma x squared. Okay, so what is given to us for the Laplace random variable, the characteristic function, which is given in the appendix A. Okay, Laplace we can try to find out from here. So in the exam, it should be given, or you can ask for the table and take it and try to write it. Okay, you can ask for the, distribution table, right? So the characteristic function is b squared by omega squared plus b squared. This is what we have for, phi x j omega, and that's what we have considered over here, right? Phi x j omega b squared by b squared minus j omega squared. So dy d of j omega, we are trying to differentiate this with respect to j omega. Then we'll get, b squared by this whole squared and internal derivative of, the quantity here j squared j omega squared. Okay, j omega squared differentiated with respect to j omega will give us the value which will be 2j omega. J omega is a single quantity. We should assume that j omega is a single quantity, or otherwise, using j over here is of no meaning. You can take it out, j over here, and try to write it also, and you'll get the same thing. Similarly, if you differentiate it twice with respect to j omega, you're going to get this function, because you have something like a by b. A by b will give you, what you call a b dash plus b a dash divided by minus b a dash divided by, b squared. If you have a by b, then differentiation of a by b will be a b dash minus b a dash divided by b squared. Okay, so or x by y, if you have, then the differential of x by y will be x dash y plus y dash x divided by, y squared, and that's what we have written over here. And once you write this, then it's only the substitution which is more important. So the mu x is nothing but this quantity which we have at, omega equal to 0. Same this quantity, or you can say this quantity, that is differential of the characteristic function, is the mean. Double differentiation of the characteristic function is the expectation of the mean squared function. Okay, and then we can use both of them to find out the value of the what you call variance, and then the standard deviation if you want. So if you substitute here omega equal to 0, you'll have 0 here, and this is 0, but however b squared minus 0 will be b squared, and numerator is 0, so therefore this quantity will be 0. Now next, if you substitute within this the value omega is equal to 0, you're going to get e of expectation of x squared. So omega equal to 0, if you try to substitute at all the places, you will get here 2b squared into b squared divided by b squared to the power 4, and totally if you try to solve that, you will get over here the value 2 by b squared. So this will be 2b squared whole squared divided by b squared to the power 4. Numerator will be 2 into b to the power of 6. Denominator will be b to the power 8, and that will give us 2 by b squared. And then you can find the variance, and the variance will be expectation of x squared minus the sigma x squared, and that will give us this value is 2 by b squared, and this value is 0 over here, 0 squared also if you write, it doesn't matter, so we'll get 2 by b squared. So this is the solution for the 58. Okay, so next we will go for 70. So problem number 70 is this: show that the characteristic function for a Gaussian random variable x with a mean mu x and a variance sigma x is this value. Okay, so whenever we write the characteristic function, it is the expectation of e to the power of j omega, the particular variable x or y. So here if you have written x, then that will give us, this is nothing but e to the power of j omega. Okay, expectation of e to the power of j omega x. Okay, expectation of e to the power of j omega x. That is what we might have written in the what you call the function, the slide set over here. Okay, in the characteristic function. So yes, so we can see that we have written phi x j omega is equal to expectation of e to the power of j omega x. Phi y j omega will be expectation of e to the power of j omega y. So we want this only, it is nothing but expectation j omega x. Okay, however, we have written the what you call, if you see the numerical itself over here, right, we are talking about the Gaussian random variable. Okay, we are talking about the Gaussian random variable. And what is the value of the Gaussian random variable for the characteristic function? We can see from the appendix. Okay, so here it is Laplace, G will come before L, and therefore we need to go back. So here we have the function fxx is equal to phi of x minus mu x by sigma x. Okay, fxx is equal to phi of x minus mu x by sigma x. So we might have to use this function to get the final value over here, and that value we have the squared over here, the squared of the function over here, and we can try to solve it and get it over there. Okay, so therefore we have here the quantity which is phi x j omega for the case of the Gaussian random variable. Okay, will be equal to e to the power of minus omega squared by 2. Characteristic function for the the value over here is minus omega squared by 2 is the quantity, and using this is nothing but e to the power of j omega whole squared by 2. This is the quantity which we will get, right? So this is the quantity which we have for the Gaussian random variable in the characteristic function, that can be seen from the appendix, or might be we can go for this and then try to check the characteristic function for the Gaussian random variable. Okay, so you can see here the Gaussian random variable over here. Phi z j omega is equal to e to the power of minus omega squared by 2, 1 by root 2 pi into this. So this is what is more important, and the rest of the thing might become 1 over here. E to the power of minus omega squared by 2. And that is what we have taken over here. E to the power of minus omega squared by 2, rest of the thing will become 1. Okay, so having taken that over there, then we have taken here y is equal to sigma yx plus mu y, and this we need to substitute. And if you try to substitute this, we need to again go for the next formula which we might have written over here, right? Okay, this is the one which we have used till now. Phi z j omega is equal to e to the power of omega squared by 2. Whether it is phi z or phi x or phi y, doesn't matter. For the Gaussian random variable, we'll get this. Further to this, having taken this, you can see that we have here, phi, what you call y j omega is equal to exponential of this. So equivalently, you can write this or you can write this. Okay, so if you try to solve it in this way, that means that you have here this function. This is equal to expectation of e to the power of j omega x, expectation of the value equal to e to the power of j omega x. Similarly, this quantity phi y j omega will be expectation of e to the power of j omega y, where y is this quantity, So if you take expectation of e to the power of j omega, y is nothing but again sigma y x plus mu y, and separate these two exponentials, then we will get this quantity over here, e to the power of j omega mu x, and then we will get the quantity which corresponds to e to the power of minus sigma x squared omega squared by 2. So if you simplify, you'll get expectation of e to the power of j omega multiplied by this. Out of that, you can take out it into two quantities, expectation of e to the power of j omega into this quantity multiplied by e to the power of j omega into this quantity. So j omega into mu y, e to the power of j omega into mu y can be taken out, right? Can be taken out over here, and the rest of the thing can be kept as e to the power of sigma what you call sigma whatever y squared over here, e to the power of sigma y y squared, expectation of e to the power of sigma y into x multiplied by j omega. Okay, so if you try to put it over here, then again, in terms of this, you are going to get this in place of you have the quantity which is omega squared. In place of omega squared, you have the quantity which is totally sigma y squared quantity. So totally we'll have sigma x squared omega squared by 2. Okay, sigma x squared omega squared by 2. So might be there is again here a print mistake. We need to write here sigma x and mu x. Okay, y is equal to sigma x plus or mu x is the value which we are written, should be written over here. There's a mistake here, and hence if you try to solve that, you will get here mu x and the sigma x squared. So this is nothing but, again, we can take out the exponential common, then we'll get these two added together, and that turns out to be this quantity. So thus we'll get the solution for the 70, which is something like this. And we can try to plot that over here. which turns out to be, with respect to this, x positive and x negative. So we are trying to write here only the magnitude. We should remember that whatever we have here is just the, angle. Okay. That is what is plotted over here. Right. Then let us go for the, 81. Shall we go for the 81? Let us see, because 81, is it corresponding to the, what you call, this one only? Yes, 81 is corresponding to this one only. This condition random variable starts from 87. Okay, so we need to write, we should have done condition random variable also today. Okay, however, we'll try to do the condition random variable tomorrow. So we'll try to finish whatever problems we have. We are left with another 8 minutes, right? So we have here problem number 81. Okay, problem number 81. So problem number 81 we have already written over here, so we need not bother. The random variable x is uniformly distributed between x equal to -2 and x equal to 3. Y is related to x using the plot shown in the figure over here. Okay, this plot corresponds to this problem. So y is related to x using the plot shown in the figure 2.16. Find the CDF and the PDF for the random variable y. Find the PDF and the CDF for the random variable y. Okay. So now this quantity, if you try to see over here, x equal to -2 and y equal to 3, uniformly distributed between -2 to 3, -2 to +3. So we should write here the PDF for x. If you write the PDF for x, PDF will be uniform, okay, between -2 to 3. So what is the duration from -2 to 3? Can somebody tell me what is the duration from -2 to 3? What is the x-axis? What is the length, or what is the breadth? Depending upon that, we should be able to decide the height. Can somebody put in the chat what is the value of the, what you call, breadth, or the distance from x equal to -2 to x equal to 3? Are you with me? Six. Is it 6? How do you get it? -2 to 3 is 3 minus of -2. 3 minus of -2. So that will be 5, not 6. 3 minus of -2 will be 5. So breadth or length will be 5. So what should be the height for uniform distribution? Can somebody tell? Total area should be how much? Area should be 1. Total area should be 1. Okay. So therefore, height, if breadth is 5, height should be 1/5 for the PDF, for the PDF of x, for the PDF of x, right? So once we write the PDF of x, we can try to write the CDF of x. How do we write the CDF of x? We need to go back here and see how the CDF of x looks like. Okay, in page number 13, we have here the PDF and the CDF for a uniform distributed function. Okay, so this is the uniform distribution function, right? So Muskan is writing something. Okay, so if you have the, what you call the y1 y2 as -2 to, in place of y1 y2 we have x1 x2 over here, and between -2 to what you call 3 we have here. So between -2 to 3, this should be a increasing value. So really speaking, -2 means it will be somewhere here. 3 means it will be somewhere here, right? -2 means it will be on the negative side. 3 will be on the positive side. -2 will be on the negative side and 3 will be on the positive side. Okay. So unless we don't write that, and then we try to write the what you call this linear, so to say, straight line over here. So we can write a linear straight line over here, right? We need to write a linear straight line over here. So if you try to write a linear straight line over here at different values, what will be the value we can try to find out? Okay. So at y is equal to -1, at y is equal to -2, okay, at y is equal to, what you call -2, the value, how much will be the value of this? Okay, that is what we need to find out. Similarly, for p of y is equal to 2, how much is the value we can try to find out? So this will be the area. This will be the area. And y equal to -1 and y equal to 2, how much values which we will get, and that can be find out directly from the what you call area to be written there, from -2 to +3, from -2 to +3. Okay. So having written that, we can try to find out from -1 to 3. You can write down here fyy is equal to 0.4 u y plus 1 plus 0.60 u y minus 2. So what you need to do is write a graph over here from -2 to 3. This is -2, this is 3. You write a straight line and then this. So at -1, what will be the area here? At +2, what will be the area here? Okay, of the triangle. Okay, area of the triangle here and area of the triangle there. Now I don't think for -1 it will be 0.40. This might be a mistake. You just find out. But however, this might be so to say at 2 it might be 0.60. You can find out. Okay, area from here to here will be again, the value will be as you go on increasing, so to say at -1 it will be a value which is 0.2. At +2 it will be a value which is 0.8. Most probably this might give 0.8 and this might give 0.2. Okay, just find out that when you try to write the graph over here, this cannot be 0.4 and 0.6, because as we write the line over here from -2 to 6, the value at -1 will be 0.2. The value at 2 will be 0.8. Okay, so equivalently we need to multiply that and try to write over here. So 0.2 u y plus 1 plus 0.8 u y minus 2 will be the value of here. If you differentiate the CDF, we'll get the PDF. If you differentiate the CDF, we'll get the PDF. Okay. So we'll stop at this. If you have any doubts, you can ask. Tomorrow we'll take up the conditioned random variable as well as some of the problems which might be over here. Okay, we'll take up the problems in the next class. Rest of the problems in the next class and the conditioned random variable. If you have any doubts, you can ask. So there is some message written by Muskan. Very good message. The only thing which I can answer from this message might be which she has written to one of her friend or to me. I don't know to whom she has written. Okay, might be to one of her friend. Is that unless you don't put effort,